Okay, ready to start? All right. Okay, we are starting the session on the investigations and predictions concerning the amplitude of the signal we are all after. The way we do this in panel 6 is the following. So we are having insight into the mechanism for production of gravitational waves and the relations with the other parameters concerning the primordial spectrum by Andrei. Okay, that's the first part. Then, following the spirit of several comments in the conference already, we go into details of physics of signals that could be manifesting themselves when the signal is very low. Okay, we have Dick Bond on behavior of physics strains and relation with entropy condensates in the early universe, and Sabino on the behavior of gravitational waves induced by scalars. So those are the things we have to worry about and to characterize, investigate coherently if the signal comes out to be very low. And then Ruth, in the end, will bring us to the main cosmological contaminant, which is known at this moment on the R, which is the CMB lensing. So we start right away, and I would invite Andrei to start the discussion.
Okay, so today I will tell you whatever slight news which appeared during last weeks. Oops, here it is. And I will start to just, before talking about R, I will talk a little bit about NS. And you see there are some news here. So the left part shows here, okay, as a Russian, I never leave home without laser weapon. And this right one, no, here. Okay, so this part shows old truth, and this one shows new truth, whichever truth we will know eventually. Okay, so the old one gives you NS 0.96, something like that. And then P and ACT together give you the numbers larger. And this is together with Daisy, and suddenly, oh, like that? Okay, good. And this with Daisy suddenly became, gradually actually, became significantly different from just Planckian results. And we were happily living with Planck for more than 10 years, and then, boom, you have something like that. So what does it mean? And actually, is it of any importance? So when I was present at the talks of different people presenting this new data, they told me, no difference, no, it's just slight shift in NS, okay? And I thought, how is that slight shift if you write that this rules out Starobinsky model by more than 2 sigma? What does it mean, slight shift? So let's discuss it a little, but to understand more deeply what does it imply, if true? Because we will see if it is true or not too early, this fresh data. So this is a picture which is often used by CMB-S4 and Lightbird to show their targets for future observations. And there are not so many distinct targets. There is this gray line, these are alpha attractors. These 2 points here, these are Starobinsky model slightly to the left, and this is Higgs inflation model slightly to the right, but approximately the same height. These purple lines specific versions of alpha attractors, depending on people somehow called it Poincare disks, that because in some extended supergravity they're related to compactification and seven different types of compactifications give you discrete number of targets here, starting from parameter alpha 7/3 to parameter alpha 1/3, and Stravinsky model is equal 1. Okay, so these are targets, and notice no targets to the right. Okay, now this boundary is approximately at 0.965, so no targets. Now somebody tells us shift here, and there's nothing to find there. Okay, so it's not really a small shift. Therefore, we need to understand, first of all, do we have any targets to the right? And yes, of course we do, but now, and what happens with us? Those who for 10 years were happy with our life and with our models and really loved them. And why did we love them? So here is, the question is, why do we love these models? What happened now? And first, before we go to all of these, is there any model which just works? Okay, which just works, whatever NS and R, can we find anything decent that would be just working? And this is just an example. So we have a polynomial with 3 parameters. What do we need to fit? We need to fit amplitude, we need to fit NS, and we need to fit R. These are 3 numbers. And one can show, and this goes back to 2007, we need to fit by this parameter, and this parameter, we need to fit these 3 parameters. So fitting AS is very easy. You just change this M, and then AS is changing. Therefore, what we need to do is to fit NS and R. And here results. I take, for example, this parameter B, which stays here. B equal to, and there was a typo, okay. It's actually for these numbers, it is 0.35, and it turned out that I could not change it today in the morning, okay. But so for this 0.35, I will have R equal to 0.001, 1%, along all the line here. And I'm changing then parameter A from 0.13 to 0.17, and I'm running NS from here, this is Planck value, to here, this is act value, to here, all the way to NS equal 1. So there is no drama. This is just stupid simple. If you want to fit 3 parameters, you solve equations, and it just luckily happens that the numerical solution is so simple. It's just horizontally slicing all the data, okay? So this means that we have it, but then why do we need anything else? Because some models happily works with just 1 parameter, which is Stravinsky model, which are alpha attractors, which I'm going to slightly discuss right now. So why do we need 3 if it is sufficient to have 1, and also if these models have some interesting physical motivation? So what is motivation, for example, for alpha attractors? And these are predictions for Stravinsky and Higgs. You take any, some words. To formulate this theory, you need to have some ideas. Like Stravinsky model started from the model R plus R squared, okay? Then when you do something with it, you transform it into a theory of R plus some specific flat potential. These theories start from scalar field with non-minimal kinetic term, which is actually natural if you say that geometry of scalar field is hyperbolic. Okay, so then this is, okay. Once you say so, you start with the theory of phi cube, and in the limit of small parameter alpha, it shows you this. You start with phi, or whatever theory, you get this. So you have something which we call attractors. In this context, you start with almost any theory. You write down anything, you draw any line with your finger, And then you push the button and you give this theory, gives you the results practically the same at small alpha limit, so it's attractors, okay? The same as Stravinsky model and Higgs inflation. And that's more exact. There are some two families of models, and depending on alpha, you go this way or that way, depending on type of models. But that's very convenient, and especially because the generality goes here more than in one choice of one parameter only. But you really put well, scalar potential, practically any, and you get the results which you wanted, or at least which we wanted before the recent data. And this shows you the specific lines corresponding to different types of compactification. And the predictions for these lines are in the range 10 to the minus 2 to 10 to the minus 3, which is very interesting. And those who remember all of these discussions, large field, small field. So if you find R at the level above 10 to the minus 2, you know that the scalar field is, which drives inflation is larger than Planckian mass. If you find R smaller than 10 to the minus 3, this does not mean that the scalar field in the theory is small. It can equally, so it's some strange kind of logic which works in one way, but not necessarily in both ways. And that is the shape of the potentials for different values of parameter alpha for all of these models. So it's all pretty simple. And that's how they look, these predictions of the models, together with ACT data. ACT is here, and this is yellow lines are so-called T models, and the red lines are E models. They are more similar to Stravinsky model, T model more similar to Higgs inflation. But what is interesting that these models actually almost touch this. Almost touch if I say that you have 60 foldings of inflation. But the number of foldings depends on the reheating mechanism. And that's one of the things which is under discussion in the literature. How many foldings do we really have? And that's a funny example, because really, usually in all models which we consider right now, well, in 99% of the models, reheating happens when the field finally falls down to the minimum, start oscillating, and minimum usually is quadratic, so that's typical picture. This shows something else. This is so-called quintessential inflation, and if you do it in the context of alpha attractors, you do the following. You take linear potential, the simplest linear potential, nothing can be simpler than that. You then imply it in this hyperbolic space, and you find the potential like that. And it gives inflation, and it gives dark energy in the same model. Whether it is completely consistent or not completely consistent, for this scenario, okay. So for this scenario, you need to have very small value of alpha, which is not appealing. So what we do next then? This is what we can do. We change we change model slightly. And what I mean slightly, in the alpha attractors, plateau is approached exponentially. In this set of models, and there are many, many different models, this limit approaches like power law. And immediately you can cover NS in the range up to 0.93. This is, I just put two of these models in this graph, and suddenly you have targets on the right part of it. This is another possibility. You just have standard chaotic inflation, but you add here non-minimal interaction with gravity, and boom, this theory fits it. Now I'm turning to string theory inflation. Well, that's the most interesting part. And this is a list of the models which was in the review published in 24. So all string inflation models which people decided at that time to discuss. This is what happened a year later. Many of these models have been ruled out because they kind of predict different things in NS and predict different things in R. So many are ruled out. Whatever remains, most of these models have R 10 to the minus 5, 10 to the minus 6, 10 to the minus 7, incredibly small. And by studying this graph, you have the following statement. First of all, if tensor modes are found with this particular value of ns, which is okay with Planck but not with ACT, and particular value of R, then this will be absolutely fantastic because it will simultaneously favor two particular models. One is stringy motivated models, and another alpha attractors with alpha equal 2. The other statement is less obvious and actually it sounds like it cannot be true. If tensor modes are found, okay? If they are not found, no statements. No found, good, okay? If they are found with any R smaller than ACT bound, but different from this particular R, if they are found that it rules all string theory inflation models which are presently known. So that's kind of a strong result just by observing this NS and R and whatever remain. Oh, what? No, there would be, oh, here, conclusions. The conclusions means precise measurements of NS can distinguish between models, such models where they approach plateau exponentially, and another set of models where they approach this like power law. Tensor to scalar ratio can take any value down to 0, absolutely no low bound, but there is a preferable and interesting range 10 to the minus 2, 10 to the minus 3. And finally, if tensor modes are found with any R below this but different from this, it will rule out all available string theorists are inventive. So all available at the moment and put into review string inflation models. Thank you.
We have now, before moving to the next talk, we have one animation, Andrei, that we are about to project. If you want to say a few words concerning this latest visualization. Yeah. What is this? Please.
That's just for fun and entertainment. This is what we study.
Microphone.
As I say, this is for fun and entertainment. This is what we study right now, some very advanced version of alpha attractors, which have some SL to Z symmetry. And it's just amazing, because what happens there is that you have this plateau, this in normal coordinates. This is infinite plateau from minus to plus infinity. And this is flat plateau, so it's perfect for inflation. All other things here looks like terribly sharp peaks where inflation is impossible. You change a set of coordinates in which you visualize it, and this is what this movie does. It just changes the set of coordinates, you just rotate around it, and you suddenly see how these sharp peaks come close, kiss the ring of the father, become equal to this, and then run again. So this is what happens. You see just stunning, and please, they're all in the left part, so don't move me to the right. Thank you.
Okay, again, so we are assuming as usual that there are no super urgent questions. We are having the discussion in the end, so at this moment I would invite the first insight into processes of the early universe. Dick, if you're coming. No. E quell'altro, quello di prima, Bond. Ecco qua, perfetto. Ok.
Anyway, obviously pleased to be here among so many friends. This is the only slide I have. It's a joke. But it gives all of the information, so in typical fashion, when I run out of time, you will have got the essence of what's going on. So this is what we usually talk about with the gravity wave production in the early universe, which is a Gaussian random field. And this is an associated curvature fluctuations, or zeta, or as I refer to as entropy fluctuations, because that's what they are, which I will get into a bit later. And the scaling between them, these two maps, is about 4 times the square root of the acceleration parameter, which is related to 1 plus w. And so the problem is we don't know what epsilon naught is, but it's small. And zeta naught is about 10 to the minus 4.3 in the observable CMB plus LSS range. You get this thing from what you might call a simple inflationary model, where you have flows down to a trough, and then you flow down the trough. So what I'm going to try and do today is to have you visualize your thoughts on the cosmic web and see that the early universe is actually just another play of the cosmic web. I call it the cosmic superweb. So think of this as a filament. And then down at the bottom here, we have the cluster that it's flowing towards. And there's a shock. We call it the shock in time. It's also called preheating or heating. It's when all of the matter entropy got generated in the universe, or at least so the model will tell us. But what I'm going to try and sell you today is that there's another possibility, which is extremely important, and yet we neglect. And why is it important to have alternatives? Because if our only target is conventional Gaussian random field R's, then there isn't that much to do with the SATs and the light birds. We need more to look at, something that's interesting and complex and yet obtainable. And so that's this side. So here is a potential. So I've given the analog of the flow in the cosmic web where this is a filament, but just think about the way the cosmic web actually is. It's got all of these saddle points as well as the basic potential minima, and so you can have a flow which then bifurcates as it's trying to find some other minima. And that's natural within the context of the early universe landscape. And so we should be looking for these things. The question is, are they in the observable range or not? And if it's the observable range, what are the observable consequences? So here's an example of that. So instead of having the flow going right down in a potential minimum, what actually happens with the various trajectories is that they flow out in a transverse direction. That's this direction. And you can see that they're expanding. It looks like it's an elastic band expanding. And then what we've usually been modeling is we let it relax towards the beginning. So continuing with the cosmic web concept of this, think of, whoops, how do I get back? That was cute. Oh yeah, okay, there we are. Think of this as a formation of the black hole. Because when you think about the formation of a black hole, you think about trajectories that in the early universe, they're propagating away, that's the expansion of the universe, and then they come back together and produce a black hole at some time later. It's not a black hole in this case, but it's a relaxation towards the original line, which if you don't do that, you end up with what you might call clusters over here, which are also the minima of Higgs potentials in another way of looking at the same thing. So what you get when you have a flow like this is you get this plus what we call primordial intermittent non-Gaussianities, which we've been studying for a very long time. However, because, wow, enthusiasm, or maybe they don't like my theory. Anyway, I'm maybe not going to be able to point to things here. these pings, which we're now calling ping pongs, and this is the ping pong theory, primordial intermittent non-Gaussianity, and primordial outlier non-Gaussianity, because these red lines here, the trajectories that are red, produce greater than 5 sigma perturbations. And so what you're going to see are images in which the non-Gaussianity is localized, its sources. Turns out the sources are clustered, which is extremely interesting. But associated with the sources, and you can see that this is a very sourcey distribution up here, there is associated gravity waves. What do they come from? They come from the anisotropic transverse traceless stress that accompanies the formation of these scalar non-Gaussian fluctuations. It isn't just that they're there, we know how to compute them, and all we need is this zeta in order to get what the gravity waves will be. And you can see, for example, or maybe you can't, that there is an association there's an association of correlation between the HTT, which is the transverse traceless gravity wave mode, and the sources that are in the scalar fluctuations. Okay, so what you get now, because gravity waves are our topic for today, what you get are strongly frozen in primordial intermittent non-Gaussian gravity waves, and they re-enter the horizon later, and then they stream. And then the issue is how much time is there for the streaming. So if they're concentrated, as those things are, then, and they don't stream very much because of a lack of time, then you will get spots for the gravity waves. If you give it enough time, you get the stochastic background. And if you let it go long enough, it becomes a Gaussian background, just like lots of waves interacting. And so the question is, and essentially the last slide is going to be showing what happens when that kind of thing comes in within the horizon. But I'm going to throw out a few numbers here, because we've heard it already talked about in this meeting. There is a euphoria, I'd say especially in Japan, about primordial black holes. It seems like half of Japan is working on primordial black holes. There you go. And I have never, in spite of the fact one of my best friends is a PBHer way back, Bernard Carr, I have never been a fan because it just seems so unlikely that you're going to get the efficiency so perfect that you're going to get something that's observationally interesting as opposed to something that's so small it's irrelevant, or so large that it dominates everything and destroys the cosmology. So the statement is that what you need for the curvature fluctuations is that it's got to be between, let's say, 0.01 and 0.1. Now look at that compared to the zeta that we have over the range of the CMB constraints that we now have, which is 10 to the minus 4.3. Now I would call that an outlier, would you? It's a huge number that you have to get. So I was very pleased being in Asia recently, and all my Asian friends are here, and we had a great time, to note that everybody is jumping up and down about using BBKS, which is applying Gaussian random field isms to...
I think because you pressed that.
How did I do that? Okay, there we go.
Okay.
See, I only need one slide. It's always the case. So, anyway, so they think the target is there, and they were using Gaussian random fields and trying to go way, way out on the tail of Gaussian random fields to get the PBHs, and that just makes no sense. You need the outliers, and the outliers have to be extreme. That's why it's ping pong theory. However, the problem with that is that the ping pongs may produce a PBH, but then there are these clustered ping pongs that cluster around the the ping pong that becomes the PBH. And those will be there, and they will have consequences. And those consequences will perhaps make the whole PBH tale a little bit artificial. On the other hand, if you don't go as far as requiring that the thing collapses to a black hole, then these things are large and interesting curvature fluctuations that will be there centered around the universe. And the question is, what scale? And the story I'm going to tell you is that the scale could be anything, but the target for today is that they could be there associated with the sats and the lightbirds and spider. And BICEP would have not been looking for this stuff because BICEP concentrated all of its observing efforts on a tiny little region and said that's universally like every place else, which is true if you're dealing with Gaussian random field, but it's not true if it's a Sorcy distribution of curvature. So that's, geez, okay. You see, that's why I needed one slide. So ping pongs are less radical than PBHs. And, well, I was going to talk about emergence, but I won't. I will continue on to see how far I can get. Oh, yeah, there we go. Okay, so this is kind of a restatement. You saw my ridiculous title, which our chair tried to get me to change, but I didn't.
With very partial success.
So this meeting is called CMB at 60. But if you're a theorist, it's CMB at 75. And if you're Bond, it's Bond at 75. I hate to say it. Forever young, right? But we have to celebrate one of the most amazing physicists of the last century, which is George Gamow. Not just because of the CMB, but it's because he did everything. He was a polymath, really impressive. And, okay, so I talked about ping pongs for zeta and W, and the way it's done is by instabilities. So you strain the field, and this is universal, right? Straining things is just like standard. I mean, it's not weird. And the reason I'll tell you it's not weird is because the reason the universe as we know it exists is because there was an instability that led to emergence and a coherence. And the coherence is usually stated in terms of H, the Hubble parameter, Hubble tensions, perhaps you could say, except in the ultra early moments. And so there's an emergence, and then what are X, Y, and Z? X, Y, and Z are expanding in the universe at large. That's instability. The universe is fundamentally unstable. You're used to thinking about gravitational instability, about things coming together. But that's a different kind of instability. That's a K-space instability, where it's the wave numbers that are coming together to go higher and higher. And so both instabilities can go on. That's how we get the black holes. So just as we have a cosmic web of X, Y, Z, we have a cosmic superweb of X, Y, Z, yes. Inflaton, yes. Transverse field, degrees of freedom, yes. Does it fit into 11-dimensional supergravity? Quite possibly. Does 11-dimensional supergravity fit into superstring theory? Well, that's the conventional view right now. And so it's an interesting concept that right at the heart of everything we do in cosmology is not the cosmic web, it's the cosmic superweb, and we are all outgrowths of that. You can see that this is becoming religious. Okay, I guess I won't be able to do this one, which is to show you how simple it is when we think about doing this stuff. We use a theory, which we played a large role in, stochastic inflation. And the way that works is that you're going to be happy that I'm skipping over these figures because they're typically bond in form. But I don't think I can skip over aspects of this unless I get a a ring around my neck, pulling me off the stage. But essentially what happens is the curvature is developed through the square root of d sigma squared zeta zeta, which is the power spectrum, times Gaussian random deviate. Tensors come from square root of d sigma squared HH times Gaussian random deviate. It's the same. That's why it's Gaussian, that what develops, except that both of them can depend upon other fields that exist, and so they can be modulated, and that's how we did non-Gaussianity with stochastic inflation.
Minus 3 minutes.
Yeah, okay. Okay, so how does this work then? I know, but I'm in the early universe. We deal with Planck times. So HTT, what you're used to dealing with is HTT free. It's like a free field. But, of course, there's another component, which is a Green's function star a transverse traceless stress tensor. And so there is this other term which people conveniently neglect and don't talk about, and that term is actually important for the microwave background at some level, at late times as well as at early times, because the neutrinos and the photons have anisotropic stress. In fact, I don't have time to tell my Weinberg anecdote, so I will just continue. I'll wrap it up. Okay, this was my favorite. I had something that was really great, but you aren't going to be able to see it. So the variety of the pings that we get, they depend upon the instability wave number, the strength of the instability, and the duration of the instability. And they could be anywhere, but if they happen to be associated with large-scale structure, then they may have an impact in the SATs, in the light birds, and even spider. So what we did in terms of the simulations is we chose a symmetry breaking potential, which is everybody's used to seeing, that's why we chose it. But we've also tried string-like potentials and many, many different potentials. And the thing that I want you to come away with is that this is generic. The results are generic. That non-Gaussianity from this mechanism is going to be there, and the question is it going to be observable or not? Okay, lots of nice figures, but we're going to do this one.
Let's go.
This is the movie, which is, we start with what you saw earlier, which is the pattern of HTT that was computed. See, they can't do this in PDF, and they don't have keynotes, so it had to be a modification of PowerPoint. You see, you start with the green one there with those non-Gaussian elements to HTT, and then comes within the horizon, our current horizon, and it propagates. And so everything that's localized starts to flow, and starts to flow into each other. And so you tend to get what will look like in the end, but still evolving, you see. You tend to get something that is approaching a Gaussian. It all depends upon the amount of time. So are you looking for a Gaussian, which is a stochastic process Gaussian, rather than the 0-point fluctuations that you're used to in dealing with gravity waves? Can we go with the next one? Okay, so this is what's happening in that simulation. Unfortunately, it's going back. I think my graduate student just repeated this, Tom Morrison. But anyway, what you see is that it starts to approach a Gaussian. And so that's basically a possibility, but everything else is also possible. So now the next one, if you can do it. The next movie. No, the next slide. This is the last slide, you'll be happy to know. And you'll be happy not to hear about the 5 papers that are about to come out after more than 15 years working on this without publishing on it. But, you know, I've now understood it. And so here is what I want you to take away. The clustered ping pong sources are generic. The positions of the instability in K-space could be anything and anywhere. At low L, that's what we've been targeting. It could be related to anomalies, and it leads to correlated QU. I was going to make a joke. I will. I know he's going to kill me, but we are very pleased, George Stathew and I, that you decided that you would name the polarization elements after both of us. BE means Bond and Stathew, right? You knew that. But it's the stupidest name, and how our community could have agreed to that is outrageous, because it's QU, it's Stokes parameters. It's just that when you're dealing with scalars in K-space, you only get Q. That's the reason that it's so-called just E, but it's really Q. And what you find when you do the gravity waves, as we did in the early 90s, just after the Kobe discovery, is that we realized that U could not be gotten rid of in K-space. That's called the B mode. But why is it called the B mode? B mode is magnetic field. And it's got nothing to do with actually how polarization works, because it's a headless rank 2 tensor. Okay, so it isn't just that it could appear in the low L world. There are 50 E-folds below the CMB plus LSS terrain where all, pardon the expression, hell could break loose because we have very little constraints. So in the 50 E-folds before reheating, which goes from about 1 over megaparsec down to about 1 over centimeter, you can get any of these things. And so you get to say, you know, while we're doing everything else, we can look for all of this stuff in our various experiments. So you can modify galaxy formation intermittently, because if you have a galaxy, you may or may not get some of these ping pongs. They can be seeds for PBHs, seeds for very massive black holes, that ultimately can be seeds for supermassive black holes. It can address the JWST issues that we heard about today. And you get weak constraints from the first stars because you can't reionize the universe too early. And at that point, I shall free you from the terrain of bondage.
Okay, thank you. All right. I'm sure that is inspiring many questions that we will about to postpone to the end. Now let me invite Sabino Matarrese to discuss the production of tensor modes out of scalar induced mechanisms and nonlinearity. Please, Sabino.
Okay. So I try to connect with previous talks for a number of reasons. First of all, the common denominator of what I'm going to tell you has to do with going nonlinear. So there are a number of results, a number of outcomes which are strictly related to the fact that you go beyond linear theory. That's the main point. Okay, if you go, whenever you go beyond linear theory, start to learn a number of interesting things. For instance, you can start with scalar perturbations, and out of scalar perturbations, second order you get vector and tensor perturbations. You can start with only tensor perturbations, and the second order you start to get scalar, vector, and tensor too. Okay? And I didn't mention, for instance, the possibility of mixing scalar and tensor, which is also quite interesting for reasons which I'll tell you later on. Okay? So that is the main point. So we are going to get a number of new phenomena. Okay? Just mention a few. I'm going to talk about B modes. I'm not going to talk about the possibility to generate the magnetic field out of that, because, of course, as soon as you start to get better modes, for instance, you also get some better modes too, okay? And also want to mention that all I'm going to tell you is classical, okay? But we are working hard in this moment to also look at the quantum version of that, okay? So there are mechanisms which generate the relevant test modes, for instance, out to the quantum version I'm going to tell you now. This is a paper that will be finishing now with Alina Mierna, PhD student in Padua, Gabriele Perna, from a PhD student in Padua too, and Nicola Bartolo and Angelo Ciardone. Okay, so intrinsic modes. That's quite important because the idea is that suppose that you go quite low in terms of the standard R, value of R, okay? Would you have a desert below that number? Do you have extra contribution, okay? What I showed in the mid-90s was the following, that because you do generate tensor perturbations, vector perturbation out to scalar perturbations, okay? There is an intrinsic B mode which arises, okay? We made this calculation with CMRs and Digorari in 2004, and we got a result which was of order equivalent to tensor scalar ratio 10 to the minus 6, okay, out to intrinsically scalar perturbation. So it's for free. It's ubiquitous. It's not avoidable, okay? Of course, it's small, okay? There was a later calculation made by, sorry, I will tell you, but let me just tell you very rapidly what happens, okay? So you take this metric, the line element with scalar perturbations and tensor perturbations too, okay, suppose, and then you can show that you produce a tensor mode this way, okay, related to the source. The source has to do with derivatives of the scalar potential, and you can also get perturbation this way. Then you use these ones, and you go to the B mode, okay? Let me tell you that there was a later paper by a group in Portsmouth who used the second order Boltzmann code song, and they got something more accurate in that respect, and the result is shown here. So basically, they say the intrinsically B mode is equivalent to 10 to the minus 7 in terms of R at the angular scale of L equal to 100, is equivalent to 10 to the minus 6 at L equal to 700. So it's not so far from our preliminary calculation. So remember, if your intrinsic B mode is below that scale, this one will emerge anyway, okay? But there is something interesting in that respect. First of all, why is there anything interesting? Because things changed recently, okay? And even this idea of scalar-induced gravitational waves, which I supported in the mid-90s, became more and more important. And now there is a sort of industry looking at that, simply because people realize that you can have more power in scalar perturbation small case on one side, which is the source of polymorphic percourse, if you like. And you can have more power on tensor modes on very last case on the other end because of, for instance, of action inflation, etc. Okay, so because of that, quantitatively things changed. Okay, let me show you this example here. Okay, this source is very sensitive to the time variation of gravitational potential. Because you do have time variation during radiation dominance because of acoustic oscillations. You have time variation in the change from reheating and radiation. And what people did, there are 3 or 4 papers in this direction, was to account for this change, to see the effect on these scalar-induced gravitational waves. And this is something which is really weird, okay? You can see here that with a Planck-fit scalar power spectrum, okay, you get something which is detectable by LISA, provided you take your parameters in a certain way, okay? I like it, of course, a lot, this idea. Of course, there is a caveat. The caveat is, you can see that here. You change a lot the amplitude on a millihertz region, okay? You don't change it on much larger scales. So in terms of effects for the CMB B mode, it doesn't have effect, okay? But that is due to the fact that I was changing the early phase of the evolution, okay? So it's promising in the sense that we learned how to possibly amplify the effect, and it's something that we have to learn and to understand more in the future, okay? There is another point which I really want to mention, connected to what Dick was mentioning before, which is this intermittency, okay? Now, let's go to the most standard tensor perturbation you get from inflation, okay? Almost Gaussian, scalar perturbation almost Gaussian, and T close to 0. And what you can show is that you get a gravitational wave background whose fluctuations, okay, are exactly log normal, okay? So you have wonderful intermittency. This is very simple to obtain, actually. It's a paper which we wrote with Alina Mierna et al. And the effect is very simple to understand because simply gravitational waves are very, very early decoupled. Okay, so you can follow the evolution by just looking at the kinematics in a very simple way. Okay, you can do this calculation non-linearly. That is only for Sachs-Wolf, I should say, otherwise it's more complicated. And you get this exact result. You get that the dense fluctuation in gravitational waves is proportional to the exponential of minus zeta, which is precisely a log normal, which gives rise to the most extreme indemnities you can ever imagine. Of course, the effect is low. Okay, it is low because the gravitational waves per se are small. But it's interesting because of the effect that Dick mentioned before, because of these can I say, characteristics of the log normal, which is the concentration in spots, in very dense spots of this. So it's something that to be studied in even more detail. Connected to that, I want to also to insist on this idea. The point is that this gravitational wave background, okay, feels the same potential wells felt by the CMB. Okay, almost exactly the same, okay? Which means that what we did was funny, we took the Planck maps, okay? We made realizations, constrained realizations of the gravitational wave background, and we compared the two, okay? So on the left, you have the Planck map. Here, you have the reconstructed gravitational wave background maps, okay? And this is accounting for the noise, in a sense. The same we do for astrophysical background, okay? Because, of course, also, the gravitational waves emitted by astrophysical sources, okay, pass through the same potential wells, okay? And this is quite interesting because you can exploit, for instance, cross correlations in that respect, okay? And this is very important. The two maps are almost identical. They're very strongly correlated simply because they are related to the same scalar perturbations in a sense. Okay, sorry. Oh, sorry, I suspect, okay. Okay, I can jump to the conclusions. So first important point, mod mixing of cosmological perturbation leads to several novel phenomena, like scalar-induced vector and tensor modes, tensor-induced scalar modes, that was originally proposed by Tomita in the late 60s. Then I wrote many papers in the 90s, and then recently people started to look very much detail in this direction for the reason which I told you before, because we discovered that you can have the possibility of much more power on small scales. Then, although these effects were originally thought to be tiny, when I proposed first these ideas in the mid-90s, people said, I mean, it's very small, okay? We don't care, it's too small. Nowadays, people are taking that so seriously, okay, that there are many papers on that, simply because of this possibility. And there is also a possibility that this kind of gravitational waves can be the source of the nanograph signal. It's one of the competing scenarios that people study in that respect. There are a couple of papers in which discuss in many details this aspect. Let me, however, go at the last topic in a very extreme case. Suppose that you have inflation without any scalar field, okay? So suppose I am the sitter, okay? People like Guy Advali, Emil Mottola, Larry Ford show that the sitter is unstable. It tends to decay towards Friedman, okay? So suppose you have that. So that we borrow these ideas, okay? We said, of course, we have the problem. The problem is that of how to generate scalar perturbations, okay? What we did was fun. We said, okay, it is unavoidable that you have gravitational waves, tensor perturbations, generated from vacuum fluctuation, okay? If you go to second order, this scalar perturbation outside the horizon generate a scalar perturbation which is scale invariant and constant, okay? Now, of course, that's unavoidable. It's there. Okay? Of course, the problem is that this scalar perturbation will typically be 2 orders of magnitude below, because the square of a tensor, which is already small. Okay? So the next question is, can you make them grow? Okay? Otherwise, you will have a result in which you have gravitational waves, let's say 10 to minus 5, and the scalar perturbation 10 to minus 10. Okay? How to make them grow? They actually grow unavoidably, because of the fact, when you look at the curvature perturbation zeta, okay, in the denominator there is something like p plus rho. P plus rho in the sitter is 0, okay? Fortunately, they don't have an infinite rho. You have a finite rho because the gravitational waves themselves do create a fluid by Hawking evaporation, if you like. And that is enough to make the result growing but finite. So, of course, we are still working in this direction. The outcome is that you can get, actually, you do get unavoidably scalar perturbation of the gravitational waves, okay, which are scale invariant, okay? They can grow, that's something that we proposed, okay? There is an issue of non-Gaussianity which has to be solved because they are typically very strong in non-Gaussian, but we are trying to understand how to, by the central limit here, how to reduce the non-Gaussianity. So it's a possibility that you should consider. But if you don't like this extreme model, remember that this effect is there. It's universal. Okay? So you should account for that. And these universal phenomena are there simply because you go beyond linear theory. There's nothing else to say. They are unavoidable. We stop here.
And I'm sure there are many questions materializing, but before concluding and going to the discussion, we invite Ruth from Geneva. She's about to tell us about the relation between the amplitude of the signal and the main cosmological contaminant so far, which is the lensing. Microphone. Microphone.
Thank you. Good afternoon. Yeah. Anyway, I want to talk about mainly about lensing. First of all, its importance for the measurement of R. I think it's going to be the main problem to solve. How can we de-lens our maps of bipolarization? Andrew has already shown us this picture and has explained us how in cosmology, you know, my particle physics friends often say, today's signal is tomorrow's background. In cosmology, we go the other way. Yesterday's foreground is today's signal. And that's exactly how we do it with lensing. Lensing is a really amazingly interesting signal. As Andrew explained us, we can actually measure the distribution of matter in front of the CMB, and that helps to break lots of degeneracies. For example, this is necessary to allow us to measure H0 with the CMB. Here you see the polarization spectrum as it has been measured recently. You see we don't have an extremely good measurement yet, but that's the bipolarization spectrum, the way it is measured right now. And the black curve is the best fit from lensing, which we would expect. So it seems to be in good agreement with the data. It is like the CMB data looked before WMAP, roughly. But you see, And this is, we have also seen it, this is the map of the lensing potential as seen by Planck, which you have also seen before. So we know roughly what the lensing signal is. Now, can we de-lens our bipolarization yet? Here, this is from the Planck paper 2018, and there are the blue points are TT, TE, and EE lensing forecasts, and the orange points are the cosmic infrared background, also from Planck, and the green points are the combination. These are used to subtract lensing, and if the B mode we would see would be only lensing, then this figure here should show us, just this line. However, what we get when we subtract the lensing from the measured bipolarization spectrum, when we de-lens it, that's what we get, so we don't get this. So the de-lensing efficiency of Planck was very bad, 20% at best, so we have to make a lot of progress here if we want to do this. as Andrew said, Andrew showed us a similar figure where they could do it better up to, I think, about 50% with newer methods. The problem is if you use quadratic estimators, they are very good if the signal you want to model is really small. So for the temperature, the lensing is a small effect. For E polarization also still we can say lensing is a small effect, but for B polarization certainly not. So there we cannot, do derivatives around zero. So the lensing is actually the dominant effect. So we have to use other methods which people are now doing and which have been developed by Julien Caron, who is here, and also by Andrew and collaborators. So this is going to be, I think, one of the most important progresses which we need to make if we want to achieve B-mode measurement at the level of 10 to the minus 3. The present limits are at the level of 0.03 or 0.04, 0.05, depending on how optimistic you are, but those are not obtained from the B polarization. Those are mainly obtained from the temperature power spectrum. So we totally need to be able to de-lens CMB maps much better than what we do now. And for that, we would need really deep experiments where we have a high resolution for a small scale power. Yeah, here you see forecasts of what we want to reach with CMBS4 experiments for the scalar to tensor ratio. They want to reach 10 to the minus 3 at 95% confidence level, or measure R if it is 3 times 10 to the minus 3 or larger with 5 sigma confidence. And all of this will, of course, depend slightly on the foregrounds and on how lensing subtraction will work, because we do need to subtract lensing at least 90% to reach this. However, I want to say a little bit something about along the line of what Anthony was discussing before, namely that lensing is a totally interesting signal. If you look at lensing at second order, you find that it actually predicts rotation. At first order, you see, if you talk about rotation, you ask rotation with respect to what? Not with respect to a coordinate system. Rotation with respect to a coordinate system depends on how you orient or rotate your coordinate system. But if you, in GR, what we consider a rotation with respect, we consider rotation of images with respect of parallel transported vectors, or here rotation of polarization with respect to the orientation of the image. Here in this little graphic, you see that whether in the first image I have B equals 0. In the second image, I have rotated slightly the image, but let the polarization exactly the same, and now you have generated a B polarization. In the same sense, if you rotate the polarization, but not the image slightly, but the other way around, you get exactly the same B polarization. These two situations cannot be distinguished. They are geometrically, physically identical. And at second order, you get these image rotations, which are rotations which you have either of the image with respect to the polarization or of the polarization with respect to the image. And if we are looking at B modes and E modes and not at the Stokes parameters, it is because these E modes and B modes don't depend on the choice of our coordinate systems. That's the difference between E and B modes and Stokes parameters. So the B modes which an experiment measures should always be the same, the B mode spectrum, while the Q spectrum of one experiment can be the U spectrum of another one, right? Depending on the coordinate system. So if this polarization rotation is really in the data and there we don't agree. I think Anthony Lewis and Anthony Challoner say it is not, and I would say it probably is. Then we will see that already with SPT 7 year. We don't have to wait for S4, fortunately. We will see it at roughly 7 with a signal to noise of roughly 7. What I do here, what I plot here, which is from this paper, is the signal to noise when we assume that we, in addition to the CMB measurements, we also have a good tracer of the lensing potential coming, in this case here, from the kappa measurement, a galaxy survey, and the infrared cosmic infrared background. Depending on what you assume for your measuring your lensing potential, you get better or worse signal to noise. So here this also is along the lines of using lensing as a really fascinating signal, because this signal would show us general relativistic frame dragging in the CMB, in CMB lensing, and I think that would be totally fantastic to see this. And with this, I put up my conclusions, if they then eventually appear. Yeah, they appear. So good modeling of CMB lensing is totally crucial for the detection and for good limits on the tensor to scalar ratio. We can hope to reach R about 10 to the minus 3. I think that's more or less realistic. And as Andre explained us, there are many models around which generate an R in this bracket where we will be able to see it. It's not entirely clear that it couldn't be much lower, because typically we say R, knowing the amplitude of scalar perturbation, R is given by the energy scale of inflation over Planck mass to the 4th power. So if the energy scale of inflation is significantly smaller than 10 to the 15 GeV, we will just never be able to see it. But anyway, I think lensing is a fascinating signal which we see in the CMB, and we will be able to learn a lot from lensing in the future with future CMB experiments. Even if we don't see R, we will also especially learn from correlating CMB with galaxy surveys, which is mainly sensitive to lensing. Thank you.
Okay, we are now starting the discussion, which we really hope will have many interesting questions and comments by the audience. We have prepared our provocative topics to discuss with you, but we really want you to start the discussion. So, anybody to start? Joe?
Yeah, so this is for Dick. With your fascinating talk at the beginning, you pointed out that primordial black hole hypothesis for dark matter was highly fine-tuned, and then at the end you had this glorious model which made many black holes and many other things. What is the degree of fine-tuning, do you think, in your predictions there?
Yeah, I would say the more likely phenomenon is you get these sources of curvature fluctuations that would then grow within a developing gravitational potential. because they will have cold dark matter associated with it and all that, and that the black holes would come later, so they would be seeds for very massive black holes, for example, that are associated with stars rather than PBHs. I mean, I know, in fact, we're going to do simulations of it too, saying this for you, of seeding some PBHs, but to think that there are lots of PBHs floating around in any of the early universe scenarios just seems rather unlikely to me, although many of my theoretical colleagues are in absolute paroxysms of joy about that possibility. So, but it just doesn't seem that likely because of the inefficiency factor in terms of making these PBHs. Because, you know, if they're forming in a big radiation field, which is huge relative to the PBH that would finally form, they will take all of that radiation and put it into a black hole. So then you have to separate them by very large amounts in order not to close the universe. Okay. I'm just repeating a story that goes back to the 70s, right?
But they cannot close the universe because it's flat.
I know. That's why they're no good.
James,
yeah.
Andrea, then Masashi.
This is a question for Sabino. When we take the Kolbe-Virus limits on scalar perturbations at scales of 10 to the 4,000 inverse megaparsecs, it seems like you can find a rather large scalar-induced gravitational wave background in the bands that we will be probing with CMB experiments. Do you think there's a problem there?
No, wait a moment. Do you refer to the last model which I mentioned?
No, I'm just saying like existing limits on scalar perturbations at 1,000 inverse megaparsecs, which
Okay.
are of course now from Virus.
Yes.
They in principle have gravitational wave background induced by scalar perturbations, as you were explaining nicely. That could be at a level that will be seen in the future. Is that a problem?
No, because I mean these scalar perturbations typically peak at smaller scales. Okay, much smaller scales. So far nobody has found any problem in that respect. I showed a plot, which is not from my paper, for this Pierce et al. Paper, in which they say for a certain range of values for the radiating temperature, you can get something which can be visible by LISA, let's say, okay? And it is still at a very low level for, let's say, the CMB, okay? Now, my point is that I cannot exclude that there are similar mechanisms able to increase the signal of this scalar-induced gravitational waves and then of the scalar-induced B mode at a level which is better than 10 to the minus 6 in terms of R, okay? So I'm not going to go beyond the standard limits for primordial gravitational waves. Okay, so I don't see any problem in that respect, frankly.
Yeah, again, I have also a question for Dick following up what Joe asked before. So first of all, if you want to explain these new galaxies with PBHs, the abundance that you need, it's very limited. In fact, we compute is about 10 to the minus 8 of the total dark matter content, so it's a very small number. Yeah. That's the first point. Now, from your theory, are you able, or would you expect, or do you have any intuition for the fact that these PBH, if they form, are cluster A, and B, if they have a mass distribution? Can you have any sensible constraints on that?
Well, there will be a distribution, but the thing is, around anything that would ultimately become a PBH would be these high curvature fluctuations, so that they're all clustered around it, and so they will be there as well as the PBH. So you won't be doing a simulation with just PBHs, at least within this class of models. And then to say that, oh, you know, I'm going to do it explicitly by PBHs, which are like these, you know, a delta function of extreme tails, that just doesn't seem probable to me. This was, I think, never taken into account by any of my PBH friends, nor anybody in Japan for that matter.
Okay, I have a question to Andre. So you showed a list of string-motivated models, and then you argue that if we have found some sizable R, tensor to scalar ratio, then these are ruled out. And then, but string theorists also proposed the so-called swampland hypothesis, and then that I assume to be a bit more generic than just a specific model. So could you comment on that? Your conclusion remains the same if we find sizable tensor to scalar ratio?
Somehow I don't know. I did not hear clearly, maybe because it's booming from that's just my Russian English is not good enough.
So okay, probably I should speak louder. The swampland hypothesis from string theory, could you comment on that? And then your conclusion remains the same if we see the sizable tensor to scale ratio?
If you're asking me about swampland conjectures in general, then in general there are so many of them that I cannot comment on them in general. There are some of them which are reasonable, but not all of them are even close to be proven. And there are some of them which I consider to be totally unproven, and one of them which I consider wrong, and that is Trans-Planckian conjecture, which I think began when we studied Trans-Planckian effects in inflationary theory, and later people realized that this is not works as originally people planned, and now they used it nevertheless, despite of everything. Yeah. But the constraint on the length of the scalar field, it depends whether you're a believer in string theory or not, and depending on what kind of believer you are exactly. But I will just give you one example. One of the swampland conjectures is that V prime must be of the V prime divided by V, potential prime divided by V, must be of the order 1. Okay? And I asked Wafa in his talk, may I ask you $1 billion question? And he, what? $1 billion question? Okay, go ahead. So I asked him whether 10 minus 2 is of the order 1 or it is not of the order 1. He stand a little bit and said, well, 10 minus 10 is not of the order 1. Okay, and that is important how people define things, because for us, whether V prime divided by V can be of the order of 10 minus 2 depends on whether R can be observable but very small, or it's just totally completely excluded, and then you do not need to spend your money for all of that. So we got the information that 10 minus 10 is not of the order 1. Deal with that.
Thank you. And now Nabila.
Thank you all for the presentation. I have a very naive question related to the contamination by lensing. My question is addressed to all specialists in lensing. So what's the amount of signal that can be attributed to contamination by B-mode lensing generated in the present day limits on R? And given this, can we really say that we have eliminated or discarded some of the models? It's here.
I think not much can now be attributed to B, to the signal of B. Our limit on R, right, is mainly coming from the temperature. I mean, if you see, if we de-lens B and then we look at what we get, so we get about 80%, which is still there, which means 80% of our present lensing B signal must be noise. I'm now talking about Planck. I think situation is much better for ACT, for example, or for South Pole Telescope, but cannot really say how good it is there. I don't have any concrete results. Maybe somebody else in the audience knows better.
Yeah, just one very quick comment. Ruth, actually, the current R comes mainly from B, not from temperature. That was when W9 and Planck delivered R constraint, 0.12. That was temperature. Then bicep Keck surpassed that. Ever since then, it's driven mainly by B. And to answer Nabila's question, lensing B mode becomes comparable to tensor to scalar ratio when R is 0.01. So current limit is 0.03, so it's still a little bit.
Okay, thank you. More questions? Okay, Nicola.
So this is a question both for Dick and Sabino, but more in general for the panel. So you were talking about nonlinear phenomena, right? So sourcing gravitational waves or scalars, and you mentioned many times non-Gaussianity. So how you could observationally catch this kind of nonlinearities in what you actually in the mechanisms that you were talking about, both for scalar and tensor modes? Do you have some precise ideas about that?
So I referred to the generality of component separation. The way you go after these things, in my view, is you build what are in effect mode functions or templates, and then you do separation of components, and there will be components that will be associated with the primordial non-Gaussianity, and there will be components that will be associated with all of the gastrophysical effects that subsequently appear, and for that matter, for the gravitational non-linearities. And so the critical issue is to find situations in which there's a separation of the modes so that they aren't too similar to each other if we're going to actually determine the amplitudes of this phenomena in the data. Then the issue is how good are the templates that we will get, and that's an issue. It's probably machine learning will be a good way to go after all of this subject because...
I knew it was popping up also here.
Yeah, right, okay. Do you want to say something?
Maybe I can add something. Of course, in both cases, I think we are going towards a different way in non-Gaussianity compared to what we were used to. So it's not something that you can still parameterize in terms of FNL with the various shapes. It's really something which deserves a different approach. For instance, suppose you have something log normal, something intermittent, okay? In this case, you probably have to figure out a way, first of all, to detect these spots, okay? Of course, in my case, the monopole was still quite low, so you have to hope to see the monopole first and then to look at these spots, okay? Let me tell you that, for instance, in the case of gravitational waves, we already know that the astrophysical sources give rise to a temporal intermittency. This is a spatial intermittency, but people are prepared to look at that. So we should really have a new strategy for new types of non-Gaussianity, which have very little to do with the previous forms that we proved so far.
Okay, thank you. More questions?
More on saying that this is not going after templates, so like FNL, local, equilateral, and so on. Are you thinking of reconstructing, I mean, the full field and looking for, you know, localized, curvature fluctuations, or I mean, I'm not clear on how you would operationally go.
Okay, of course, it's something which should be completely new, so I don't have a way of saying this. But let me tell you, what is FNL? FNL is a situation in which you basically tailor expand your object, okay? You have a Gaussian term and some
local
other.
at least.
For instance, in the case of the inflation without the infinite dimension, we don't have the linear term, okay? So we start with the quadratic term. And that, of course, is completely different. It's sort of an infinite FNL, if you like. So in that case, probably, in order to reduce this tremendous level of uncertainty, what we have in mind is to consider the fact that there are many different fields with regard to the same fate. So through the central limit, you should be able to reduce it, okay? But in full generality, I think that this issue, also the one mentioned by Dick, is so different from the past that we should really change strategy.
Yeah, my view is that it's more generic. The FNLs that are predicted in standard theories are actually really pretty tiny if you go back to Maldacena, et cetera. And so we refer to those as perturbative non-Gaussianity. And this is different because it's localized. And then the issue is, how do you measure the localized? Well, you're looking for sources, except that there's sources that don't necessarily have to be associated with conventional galaxies that would form, for example, in a standard cosmology. So they could be here, there, or anywhere. And let me give an example of that, because we played with this before. How would you get the cold spot by this sort of mechanism, the WMAP cold spot? And the WMAP cold spot is about 4.2 to 4.4 sigma, which means that you can't get it from Gaussian sources. So, but you could have a situation where you've got a little bit of up from the Gaussian underlying structure, and then you happen to have one that sits on top to raise you up. That's like putting a source on the microwave sky that is going to give you some places an enhancement and some places a decrease. And it's the enhancement that would give rise to this. So it'd be like a constructive interference that would be kind of random.
Yeah, but still, I mean, this is, I mean, this anomaly, let's call it, it's the only one, or one of the rare one we found.
Well, no, that's the problem with the low L world. We have, in my view, we clearly have anomalies at low L, but there isn't a grand unified theory of anomalies, so that things that are like 2.2 sigma build up into 3 plus sigma. So, you know, there are the low L, less than 10 anomalies that go through the plane of the galaxy, and then there's the cold spot, and then there are other cold spots, and hot spots for that matter, but they're kind of buried in the plane of the galaxy, which means that you don't really get used to them. So it's the rare event aspect, which is unfortunate, but you know, that's what we've been dealing with all along with cosmic variance limited problems, because there aren't that many modes at low L.
Exactly. I mean, that's why I'm sort of pushing on this, because precisely we had, I mean, all the anomalies, which are well documented, where Planck has only confirmed the previous detection by WMAP, are submitted to the curse of, you know, small number of modes where, you know, we have essentially low significance. But then when we go to higher, I mean, smaller angular scales, there are no such things, or at least to my knowledge, that pop up as evidently. So what is a handle? I mean,
it means you have to go deeper in order to, if you're going to pick this stuff up. I mean, the problem is
higher signal to noise. This is what you mean by deeper.
Yeah.
So you would say that there are, in the statistics, so you would see some tiny fluctuations.
Well, if these things occur, I mean, you know, there are only 9 E-folds in the observable range with the CMB, and LSS for that matter, which means that it's a range, and if you go into somewhat higher L, so for example, there's a regime in which Planck couldn't get there, but SO will. But it's not going to go really deep either, that is to say, to really high L.
And then you'll get another curse where you'll get much stronger, you know, non-primary signals that will swamp the signal, right? I mean, the component separation problem will get even worse at very small L. I mean, you know, the non-primary.
Well, yeah, but what if these things are there?
Well,
are you going to
that's why
say
I'm asking,
they
how
can't
do
be
you get
there because I can't do appropriate separation?
I'm asking, well, operationally.
Well, operationally, it will depend somewhat upon the nature of the non-Gaussianity, but the general nature of this thing that I was describing is, in my view, quite ubiquitous. So it's going to be somewhere, and the question is, there may be many different places, but it is disturbing that things look so LCDM-ish with Gaussian initial conditions throughout our observable range, except at low L. That's our, you could say that's the Planck curse.
Yeah, so I take that what you are making a plea for is very high angular waves, full sky, with a very large frequency range so that we can deal with all of this. So that looks like future CMB mission with a 5-meter telescope.
Something like that, yeah.
Or on the moon, of course.
We have also Douglas.
Yeah, I'm sitting here quietly, but somebody said anomalies. The cold spot is not 4 sigma. That is completely incorrect. It's 4 sigma if you pick the test after looking at the data. So you have to pick the filter size, the shape of the filter, etc., and then it's 4 sigma. If you marginalize over tests, it totally goes away. There are no low L anomalies that stand up to marginalizing over tests.
I actually don't think that's right.
It's published. It's completely clear.
It doesn't matter if it's published. It isn't right. That is to say...
Well, I've published it, so it's completely clear. Is that better? But this is, I mean, all of these low L anomalies are interesting. They're all an indication of something, and that's why we need independent polarization data at low L, because then we can test the things with a test that's already given, and therefore it doesn't suffer from the a posteriori statistics
We
trap.
look for structures by RG flows on the maps. And you're saying you can't do that because no matter how big my thing is, it's going to be compatible with Gaussian. And I don't think that's right.
More satellite?
Yes, so talking about anomalies, okay. I think we have to pay attention to these anomalies, not because they are 4 sigma, because they are not, I agree with you, but they are not on just 1 sigma. They are in between.
What's 1 sigma?
It's not 1 sigma, it's more than that. So it's around the anomalies. I'm talking in which one? There are several, I mean, including the cold spot. But there are
the cold
also
spot, what did you say, the cold spot is noise?
No, I'm saying that there is anomaly, but the anomalies, all of them, I consider to be around between 2 and 3 sigmas, no more than that. All of them. So another thing, sorry? They are this kind of Frankenstein or whatever you call it, but it's what it is, yeah. And then I agree that it's very difficult to go beyond this unless we get independent data. And this independent data is polarization.
No, that's an extremely important point. The unfortunate thing is that where the cold spot exists is kind of a trough in the polarization. And so the prediction is that it isn't anywhere near 4 sigma, it's a little over 2. Or at least it's my prediction. Obviously, so Douglas is in complete disagreement.
We are going to publish a paper on this about with Liebert. So just in a few weeks, I suppose. And we really study this, and I think we can say more with Liebert on this. But you will see the paper.
Well, you all signed off on isotropy and statistics, which had all of these numbers in them. So.
It is. Okay. More urgent points before dinner. So we might go to the things. The wrap-up message is that tomorrow we are going to hear more precisely along these lines. We're not done with CMB at 60 because the curl mode has to be mapped accurately from the quadruple to thousands in multiples. And so we need appropriated probes to do that. And tomorrow we are going to have a discussion concerning that complementarity and where we are on probes for observing this part and for making the last observation of the signal that is missing. Okay? And with that, we thank you, the speakers, the audience, and we move to dinner, which is. Does anybody know where the dinner is? Yeah. Okay. 8 p.m. in a restaurant.
So dinner is written in the email you should have received. and it's